In this particular video we're looking at the production and use of radioisotopes. The first thing that we need to consider is the fact that anything above uranium on the periodic table is synthetic. It has been manufactured. So that means all of these and all of these are manufactured. They do not naturally occur. They are called transuranic because they are above uranium. So that's from neptunium, from atomic mass 93 up. They're all synthetic. They're called transuranic elements. Transuranic elements are produced in one of two ways, either in a nuclear reactor or in a particle accelerator. That could be something like a linear accelerator or a cyclotron. The first way of producing transuranic elements that we're going to examine is through the use of a nuclear reactor. Nuclear reactors are designed to release neutrons, which are then captured by a fuel source. So in this particular example, in the first one that we're going to look at, we've got uranium-238. It is our fuel rod in a nuclear reactor, and the nuclear reactor releases neutrons, and those neutrons are absorbed into the uranium. And in this case, they're producing uranium-239. So once again, a nuclear reactor is designed to release neutrons, and they often use californium-252, which releases neutrons. They release neutrons which are then absorbed by other substances. Those other substances can then undergo various decays, producing transuranic elements. So for example, in the example here, we've got uranium-239 being produced in a nuclear reactor from uranium-238, which is naturally occurring. The uranium-239 then undergoes beta decay. We know it's beta decay because we have an electron being produced. They undergo beta decay to produce neptunium-239. So neptunium-239 is produced by the beta decay of uranium-239. Now, that neptunium, which is now over here, that undergoes beta decay to form plutonium-239. So the neutron capture of uranium-238 first produces neptunium-239 and then plutonium-239 through two beta decays. And this is just one example of neutron capture in a nuclear reactor producing transuranic elements. The second way of producing transuranic elements that we're going to examine is through the use of a particle accelerators. Now, a particle accelerator is just a collider. It slams atoms of one element into atoms of a different element. Now, the first thing that's required is to ionize the particle that we're going to accelerate, turn it into an ion, and this diagram actually shows negative ions being produced. So there's some examples. The particle accelerator uses alternating positive and negative electric fields to accelerate the particles. So for example, in this case here, we've got a negative charge. So that's our particle that we want to accelerate. It is being repelled by this negative field and attracted to this positive field over here. So it accelerates in this direction. When it gets on the other side of this drift tube, so we're talking about down here, the polarity of the tubes is changed. So instead of being a positive, it is now a negative. It is now repelled, because we've got a negative ion here, it is now repelled by this negative field and attracted to this positive field. So again, it is accelerated this way. Once it's past this spot, it gets to this spot. The fields are again swapped. So I've got a negative field here, which is repelling our negative ion. We've got a positive field here, which is attracting our ion. And once again, the particles are accelerated through the tube. So these two diagrams are just showing that the fields in the drift tubes are swapped as the particle goes through. So again, the particle is both being repelled and being repelled by the drift tube behind it and attracted to the drift tube ahead. And that's how it accelerates through. And then they're just slammed into a sample, which would be at the end of the particle accelerator. Now a linear accelerator is just a particle accelerator which is in one long line. Some examples of radioisotopes produced in a particle accelerator are the production of californium-250. And in this case, we've got a uranium-238 atom, and it's being slammed with a carbon atom, a carbon-12 atom. So the carbon-12 would be accelerated in the linear accelerator and slammed into the uranium, and if they fuse, we get a californium atom being produced. So we have a transuranic. We know it's transuranic because it is larger than 92. Another example, very similar, if we have a nitrogen atom being slammed into uranium-238, we're getting Einsteinium. If we get an oxygen atom being slammed into uranium-238, we're getting a fermium-254 atom being produced. Okay, to examine some commercial radioisotopes. Now, a radioisotope is just a radioactive isotope. They are produced in both nuclear reactors and cyclotrons. These are some examples of radioisotopes being produced in nuclear reactors. All right, so we've got uranium-235. Uranium-235 is said to be fissile, which means when a neutron hits it, it tends to split apart. It fissions into, in this case, we've got krypton or barium. It also produces 3 neutrons, plus gamma waves, plus enormous amounts of heat. Now that is just one example. The fission of uranium-235 produces randomly different particles. Now in this case we've got krypton and barium being produced. Another example is here, and in this case we're getting molybdenum-99 being produced, as well as tin-134, plus 3 neutrons, gamma waves and heat. But the products are varying depending on the actual collision. So the different collisions produce different particles, different fission products. Here we have a diagram of a cyclotron. A cyclotron is very similar to a linear accelerator. It uses alternating electric fields to accelerate particles, but in this case the particles start in the middle and magnetic fields are used to bend the particles, the charged particles, so that they whiz out and bash into the target, which is up around here somewhere. So it's the same idea, alternating electric fields and accelerating the particle, but magnetic fields make the particle bend, and this means that a much smaller apparatus is needed. We've got an example here of oxygen-18 being bombarded with a proton. Now a proton, you've got to remember, a proton is just a hydrogen ion. So we've got a hydrogen ion slamming into an oxygen, and that proton is absorbed by the oxygen and it's producing fluorine-18. Now in the case of producing fluorine-18, it's normally a case that oxygen-18 enriched water is bombarded with a proton, and that produces the hydrogen fluoride, which happens to have fluorine-18 instead of your normal fluorine. Now the fluorine-18 is then used in what's called positron emission tomography, and it decays by producing a positron. Now positrons are beyond the scope of the HSC chemistry course, but that is just an example of a very commonly used radioisotope produced in a cyclotron. There are many and varied industrial uses for radioisotopes. 2 that we're going to examine at the moment are stopping the infestation of the Queensland fruit fly, and then we'll look at thickness testing. Now the Queensland fruit fly scientists are trying to contain them to Queensland. When an infestation of the Queensland fruit fly is found in New South Wales, they rear a whole stack of the fruit flies in the laboratory, irradiate them with a gamma source, and effectively cause them to be sterile. They are then released into the wild in the same area as the infestation, and the sterile fruit flies breed with the invading fruit flies, and therefore they don't have any offspring, so that the infestation is then halted. And this irradiation happens at Anstone in New South Wales. Thickness testing is another area where industrial radioisotopes are used. We have got a beta source, so cobalt-60 for example could be used, and as the beta particles go through the sheet material here, the amount of beta particles that get through is proportional to the thickness of the actual sheet material, and a reading then controls how far apart these rollers are. So if we're getting too much product going through, too much beta particles going through, then our sheet material is too thin, and therefore these rollers will change in their width apart. There are also very many medical uses for radioisotopes. At the moment I'm just going to look at technetium-99m, which is used for diagnostic imaging. Now technetium-99m is produced from the beta decay of molybdenum-99, and molybdenum-99 produces technetium-99m. So we have molybdenum-99 giving off an electron producing technetium-99m. The technetium-99m then undergoes gamma decay to produce technetium-99. Now the 99m bit means it's a metastable isotope, just means that it's got a packet of energy, effectively the energy that is released in this gamma ray, stuck in the nucleus. So the beta decay of the molybdenum produces a beta particle and also a gamma particle, but the gamma particle, the gamma ray, is held within the nucleus of the technetium, and that's why we've got an M, and at some later stage that gamma ray is released and we are left with technetium-99. Technetium-99m is particularly useful because it has a half-life of just 6 hours, which means that when it is inserted into the body, within 6 hours the amount of technetium has halved, another 6 hours, so after 12 hours it's a quarter, after 18 hours it's an eighth, etc. So it rapidly is reduced in concentration in the body. Technetium-99m, or technetium, also has multiple oxidation states so that it can be tagged onto biologically significant molecules, which then go to an organ of interest, and they release the gamma rays, or they're releasing the gamma rays the whole time, but if they accrete in an organ of interest, we can actually take an image of that organ using a gamma camera. So for example, if we wanted to examine the liver, we would tag some technetium onto a chemical that naturally goes to the liver, inject it into the bloodstream, wait until the blood has had a chance to, the technetium-99m and its chemical has had a chance to accrete in the liver, and we get a gamma camera, and we can, in a non-invasive way, diagnose liver problems. This particular document, you don't have to remember all of this, but it has a whole stack of different chemicals to which the technetium can be attached to make their way to specific organs of interest. So for example, if we wanted to do some imaging of the liver, which is what we were just talking about, we would attach the technetium to albumin. It then accretes in the liver, and we can take an image of the liver. If you wanted to do some brain imaging, you could attach it to this particular chemical or this particular chemical. If we wanted to diagnose tumours in lungs, we could add it to this particular chemical. So once again, technetium is attached to many different chemicals which just make their way to the organ of interest and therefore allow non-invasive medical diagnosis. There are quite a few ways that we can detect radiation. So the simplest one is photographic film, then we've got a cloud chamber, a Geiger counter, and a scintillation counter. These particular diagrams show some radiation sources, so there's that particular one, there's another radiation source, another radiation source. They are sitting on this plate which has photographic film within it. So for example, this particular radiation source has produced that exposure on this bit of film which is inside that plate. This one is produced from this chunk. This little bit there is produced from there. So photographic film will be exposed by radiation sources. It's one way to detect radiation. This particular property is used in film badge dosimeters. So if you are working somewhere where there is radiation, you have to be monitored as to your exposure. If you have too much exposure, then you can't work there any longer. So this particular unit is clipped onto your clothes. A strip of film is lined in here, and the whole thing is folded over. We've got a clear window, so if there's any radiation at all, it'll just come straight through the clear window and expose the film. These different plates have different densities or different stopping power in regards to stopping radiation, and if the bit of film behind these plates is exposed, you can get an idea of just how much radiation there is. So one of them will be exposed with only a small bit of radiation, that'll need more radiation, that'll need even more radiation. So again, it's just a way of seeing how much radiation you've been exposed to. A cloud chamber is another way of detecting radiation. In this particular chamber here, we've got a supersaturated solution of water or ethanol. When ionising radiation, so that's a radiation source, when ionising radiation goes through that vapour, it ionises that vapour, and those ionised particles then act as nuclei about which condensation forms, or in other words, they act as nuclei about which tiny weeny little clouds form. So that is why it's called a cloud chamber. A magnetic field can then be applied across the cloud chamber, and depending on the deflection of the particles, you can work out whether you've got alpha particles, beta particles, etc. A Geiger-Müller counter or a Geiger counter works by incident radiation coming in through this window. As it comes in, it ionises some of the argon gas found in this chamber here. We've got a high voltage being applied across both the outside and this middle electrode, and the ionised particles are attracted towards this electrode, and as they move towards the electrode, the ionised argon gas molecules bump into argon gas atoms, bump into other argon gas atoms and ionise them, and cause a bit of a cascade of ionised gas particles hitting this electrode, which constitutes a pulse of electricity, which is then detected by this particular counter, and we get a reading for how much radiation there is. A scintillation counter is the last way of determining radiation that we're going to look at. A scintillation counter has some sodium iodide crystals. When ionising radiation hits these crystals, the actual crystal gives off a photon of light. That photon of light then hits a photocathode, and that photocathode releases electrons. Those electrons go through a photomultiplier tube, so we're getting an increase in the number of electrons moving. They hit the anode, and that anode is then hooked up to an external circuit, and that electric pulse is detected and counted. Last thing we need to look at is the recent discoveries of elements. The vast majority of new elements are being produced in linear accelerators or particle accelerators of some sort. So we're looking at ununpentium. So ununpentium was produced from calcium-48 and americium-243 colliding to produce ununpentium, and ununpentium then decays to give ununtrium. So we've got ununpentium going to give ununpentium with 3 neutrons, and then that ununpentium decays by alpha decay to give ununtrium. Ununpentium was first produced by the Joint Institute for Nuclear Research in Dubna, Russia in 2004.